It all started when someone gave me a broken Pripyat radiation meter from 1991 and asked if I could bring it back to life. Since I'm still learning electronics, I saw it as the perfect opportunity to improve my repair skills. When I powered it on, absolutely nothing happened. So I took it apart and quickly realized that it had either been flooded with water or stored in a very damp environment for years. Many of the PCB traces had corroded away, along with the leads of several electronic components. The damage was so severe that I had to completely remove the most heavily corroded section of the circuit board, clean everything, rebuild the damaged traces, and solder in new components according to the original schematic. And in the end, the radiation meter came back to life. I've taken this exact model of radiation meter with me to many of the most iconic locations inside the Chernobyl Exclusion Zone: Pripyat, the Duga radar, the abandoned river port, the Buryakivka radioactive vehicle storage site, the Ferris wheel, the Central Square, the famous radioactive excavator bucket, the abandoned hospital, and many other places. And that's only a small fraction of everywhere I've explored. Since I'm planning another trip into the exclusion zone, I wanted something much smaller, lighter, and easier to carry. So instead of buying a new one, I decided to build my own compact Geiger counter from scratch. After searching online, I found a well-documented Geiger counter project called ArDos. I removed two optional modules, the flashlight and vibration motor, because I didn't need them. Then I made a list of all the required components and chose one of the PCB layouts that was available online. I printed the PCB pattern onto glossy photo paper using a laser printer, cut it out, and transferred the board dimensions onto a piece of copper-clad PCB material. After that, I cut the board to size with a utility knife. Once the copper surface was thoroughly cleaned and degreased, I carefully positioned the printed pattern on top of the PCB and secured it with masking tape to keep it from moving. To transfer the toner onto the copper, I pressed it with a household iron at maximum temperature for several minutes. The first attempt didn't go very well. The toner transferred only partially, most likely because I didn't apply enough heat. On the second attempt, however, the transfer came out almost perfectly. Any small gaps were touched up with a permanent marker. Next, it was time to etch the PCB. For the etching solution, I mixed 150 grams of water with 50 grams of ferric chloride, stirring until the powder had completely dissolved. Once the solution was ready, I submerged the PCB and waited for the exposed copper around the toner to dissolve. In my case, the entire process took exactly 30 minutes. After rinsing and drying the board, I drilled all the holes for the through-hole components while it was still easy to handle. The final preparation step was to remove the toner with a suitable solvent and tin all the copper traces with solder. This protects the copper from oxidation and makes soldering the components much easier later on. Now it was finally time to start populating the PCB. I began with the SMD components, starting with the 10 megaohm and 2 megaohm resistors. Since this was my first time soldering components this small, I carefully inspected every solder joint before moving on to the next one. Next came the through-hole components. I installed the transistor for the audio circuit and soldered in the mounting clips for the Geiger tube. By the way, these clips can easily be salvaged from standard fuse holders. After that, I soldered the headers for the Arduino, installed the transistor that reads pulses from the Geiger tube, and added all the resistors according to the schematic. If you don't have a resistor with the exact value you need, you can combine several resistors together, just like I did. Then, I added a red LED to flash whenever a particle is detected, installed several capacitors, push buttons, diodes, Zener diodes, and 2 header pins for disconnecting the high voltage section during testing. I also installed the buzzer that provides the audible click each time radiation is detected. With the remaining components in place, I soldered in the Arduino Pro Mini 16 MHz along with a Nokia 5110 LCD. According to several online forums, an SSD 1306 OLED display can also be used as a replacement. Now it was time to build the most important part of the entire project, the high voltage converter. This is the circuit responsible for generating the 400 volts required for the Geiger-Muller tube to operate. To build it, I took a defective LED lamp power supply, removed the inductor, disassembled it, stripped off the original winding, coated the ferrite core with fast-drying insulating varnish, and prepared a simple setup for winding a new coil. According to the schematic, the coil should have 600 turns of 0.1 mm wire wound on a dumbbell-shaped ferrite core with end caps measuring between 6 and 8 mm in diameter. The core I had measured 10 mm, so I assumed I could get away with fewer turns. In the end, I managed to wind around 550 turns before I completely ran out of wire, so I decided to leave it as it was. I soldered the wire to the second terminal and insulated the finished coil with heat shrink tubing. To turn the inductor into a transformer, another winding had to be added on top, just 4 turns of thicker wire. I used a single conductor from an Ethernet cable, wound 4 turns around the coil, and coated them with insulating varnish so they wouldn't unwind. Of course, there's a much easier way to do this. You can simply buy a ready-made 10 millihenry inductor and add the 4-turn primary winding yourself. I actually had several of those available, but I really wanted to try winding the transformer from scratch. And honestly, the result exceeded my expectations. Those 550 turns produced an inductance of 10.2 millihenries, which was almost exactly what I needed. With the transformer finished, I moved on to the power supply. The original design uses a compact TP4056 charging module, but the one I had was physically larger and didn't quite fit the PCB. On top of that, I planned to use only a 400 mAh lithium-ion battery, which would require changing one of the resistors on the charging board to reduce the charging current. Since I didn't have the correct resistor, I decided to use the charging module from a cordless soldering iron instead. It was already designed for a battery of similar capacity. It might not look quite as clean, but the charging current is now perfectly matched to the battery, which is much more important. After soldering the charging module onto the PCB, I decided to flash the Arduino before installing the battery. I had already left programming pins on the board for exactly this purpose. Unfortunately, ordinary DuPont jumper wires couldn't reach the pins properly, so I improvised by cutting apart an IC socket, soldering 6 wires to it, covering everything with heat shrink tubing, and adding a little hot glue to make the adapter more reliable. Following the schematic, I connected the board to a USB ASP programmer, downloaded the firmware from GitHub, and, with the help of YouTube tutorials and ChatGPT, finally managed to upload it to the Arduino. It definitely wasn't successful on the first attempt. This was my first experience working with Arduino, so there was quite a bit to learn. But after a little troubleshooting, everything worked exactly as it should. At that point, all that was left was soldering in the battery. Or so I thought. After fully charging the battery, I powered up the device for the first time, and absolutely nothing appeared on the display. The Arduino itself had started successfully, so after some troubleshooting, I discovered that my LCD module used a completely different pinout. To test that theory, I removed the display, connected it using jumper wires according to the correct wiring diagram, and, as you can see, the display immediately came to life. So, I removed the original header pins, replaced them with individual wires taken from an Ethernet cable, arranged them to match the display's pinout, and soldered everything back together. Now, everything was working perfectly. Next, using a homemade high-impedance divider, I measured the output of the converter to see whether it was actually producing the required 400 volts. And it was. The divider measured 40.6 volts, which corresponds to approximately 406 volts at the converter output. That confirmed my homemade transformer was performing exactly as intended. However, once I installed the SBM20 Geiger tube, I realized the entire device had become larger than I wanted, so I decided to make it more compact. I replaced the tube with another SBM20, this time one without the external metal leads. If you can't find this particular Geiger tube, you can also use one of the inexpensive Chinese tubes available on AliExpress. You'll only need to adjust the calibration value in the firmware or device settings. I removed the battery, marked a cut line on the PCB, and cut away the unused section of the board. I also decided to upgrade the battery to a 650 mAh lithium-ion cell, since the original 400 mAh battery no longer fit the layout I had in mind. As a result, the radiation detector became 8 mm shorter while actually gaining a larger battery. I also removed the unnecessary Geiger tube connector. designed a custom mounting bracket for the tube, printed it on my 3D printer, and installed it in place. Instead of using removable contacts, I soldered the tube leads directly to the PCB. I did the same with the battery connections to save even more space. After that, I thoroughly cleaned the PCB with isopropyl alcohol and a toothbrush to remove all remaining flux residue. Then, I reconnected the high-voltage section using a jumper and moved on to the final stage of the project, designing the enclosure. I started with a simple sketch on paper, then modeled a 3-piece enclosure consisting of a front panel, a back panel, and a removable cover for the Geiger tube. I also added decorative details, control buttons, and a dedicated power button. The finished enclosure turned out compact and surprisingly elegant. It actually resembles a small notebook or pocket-sized book. Once the design was complete, I printed all the parts on my 3D printer and assembled the final device. Now, it's finally time to see how it performs. After powering it on, the detector immediately displays the current background radiation level. The firmware is currently running in Russian, but when flashing the device, you can choose either Russian or English. Holding the down button adjusts the display brightness. Pressing the up button lets you change the measurement interval, anywhere from 60 seconds to 60 minutes, as well as view the maximum recorded radiation level and the accumulated dose. Hold right mouse button opens the main menu. I won't go through every option in detail, but the settings menu allows you to customize the detector however you like. Overall, the firmware offers a surprisingly wide range of features. The debug menu displays the main operating parameters of the system and allows you to fine-tune them for maximum accuracy or adapt the firmware to work with different Geiger tubes. To test the detector, I used these inexpensive stickers from AliExpress that are supposedly designed to protect against electromagnetic radiation. The funny part is that they actually contain a tiny amount of radioactive thorium-232. The radiation level is very low. But if you place the detector directly on the stickers, it consistently shows around 60 microrentkins per hour. As soon as the source is removed, the readings quickly return to normal. Like any Geiger counter, the longer the measurement time, the more accurate the result becomes. And if even higher sensitivity is needed, the design allows you to add a second Geiger tube without making any changes to the circuit itself. Thanks for watching.